and I work for the Met Office Informatics Lab as a scientific software engineer. The Informatics Lab is a team within the Met Office that is a cross-disciplinary team focused on the connection between science and technology and design, and we do a lot of work in the data science and machine learning space, and we contribute that to the Environmental Futures and Big Data Impact Lab, which is a partnership between all those organizations you see on the screen there, which I won't read through all of them. But we focus on helping small to medium enterprises in the southwest of England use environmental data and harness big data for their businesses. So on to today. First, let's recap what was in part 1 of Introduction to Python for Data Analysis. So if you're registered for that, you should get the recording. Otherwise, the recording will be at some point available on YouTube. But just to quickly recap, we started talking about why Python and why is it good for data analysis. And we talked about how as a scripting language, it's very easy to get started and lots of tools available to use for data analysis. It's widely supported and lots of kind of community help. And then we went through 4 Jupyter notebooks last time, firstly covering the basics of Python, how you do conditional statements, repetition statements, and code reuse in terms of if statements, for loops, and functions. Then we looked at some native Python data structures, such as lists and dictionaries. We looked at data types, so tabular and gridded data. We'll look in more detail again at tabular and gridded data in this session. Then we looked at how with Python you operate natively on data, and then also some visualizing of data as an important way to gain insight and start your analysis process. So that was our last session, session 1. Today, we are going to then build on that by looking at how you can do those things, but in the context of data models and using higher level third-party libraries to do all those things in an easier and more intuitive way, and also in a way that scales up to big real-world data sets. And we'll look at that in the context of some real-world data sets. I'll be using some weather and climate data set examples that I've taken from the Met Office to show you how we can actually use these techniques for real problems. So just a reminder, all of the code that I'll be going through is available on that repository link there. We'll be sharing these links via email after the session as well. And the materials here have been inspired by some existing courses online, particularly software carpentry and data camp. And I recommend that if you want to get started with this after the session, going through those courses is very worthwhile in helping you get started, and working through those examples will give you the knowledge to get started with the tools for data science. So our focus today is then on data models. So you might say, what is a data model? So this text from Wikipedia, I think, sums it up for me. A data model is an abstract model that organizes elements of data and standardizes how they relate to one another and to the properties of real-world entities. So the idea with data models is, in our last session, we were looking at kind of raw numbers, and this is about data models all about saying these raw numbers mean something in the real world, and adding in certain elements to that so that the data model is kind of self-describing. You can look at it and you can see what those numbers really mean, how they relate to another, and how you can operate on it. So it combines, in order to make that happen, the raw data. So that, let's say we're talking about a weather data set. That data could be the actual temperature values for an area of a map. So that temperature values in Celsius. So the metadata then tells us what that data means. So I've said our numbers could represent temperature in Celsius. That's the fact that it is measured in Celsius is part of the metadata, the unit of the data. We might want to know what range of latitudes and longitudes it refers to. We might want to know what time it was measured at. All that's metadata, describes the data, and so it gives us a meaningful data model. We also then describe the relationships between it. So in the case of temperature, we might talk about how temperature relates to humidity or dew point temperature or wind. And also there's some standard operations we can do that make physical sense in terms of that data. So we might be able to find a mean temperature or a maximum temperature. Those are meaningful operations to perform on the data. And that is also part of our data model. So data models are a very important concept when you're doing data analysis, because you have taken in your data from some measurement or tracking of some kind, and it represents something real in your business. And your data model is essentially saying how these raw numbers tell you something about your business. So it's really the foundation of data analysis, is to have a model of what that data represents. So now we're going to look in the code in some Jupyter notebooks about how data models are actually used to do data analysis in Python. So let's try and find my code. So a reminder, this is the repository. These 7 notebooks are all available here. From 1 to 4 is from the last session. 5 to 7 are the ones we'll be going through today. Just a note to say, at the moment, there was a slight problem with sharing the data that these depend on. So you can see the code, you can run the code, but the actual data sets are not available. I'm busy sorting that out. So hopefully by next week, the data should also be available for you to run those notebooks yourself, but we will let you know when that is the case. But for now, I've just got a snapshot for myself, so I'll be able to run through. But hopefully sometime next week, you will also be able to run through the notebooks yourself if you would like to. Right, so let me clear my notebook. So as we said, a data model, we've gone through all the building blocks in Python for how you work with data, but we want to work with our data at a higher level. And so we've covered these operations, loading our data, performing operations on it, calculating statistics and visualizing it, but we've done it all very manually. And some of the disadvantages to the approach we've shown in notebooks 1 to 4 include the fact that you have to implement a lot of the things yourself. Things that people have implemented previously, you have to do again. So there's a lot of kind of reinventing of the wheel. And the more you do that, the more error prone your code is likely to be. Rather write something once, get it right, and then reuse it for reliability. So that's not a great way to do it. So rather, we want to reuse other people's code, and particularly we want to use code that works at a high level so we can understand things in an intuitive way in terms of a data model. So as we said in the introduction, our data has not been self-describing, it's just been a grid of numbers which we have to somehow, through some external means, understand. Data models, as we said, gives us some way of making the data a bit more self-describing. So you look at the data and see what it does. So as an example, just to start with, we'll just recall one of the examples we did previously. We have some weather data in a CSV file. So this is tabular data. Tabular data, just to recap, is where it's a bit like a table where each row represents a measurement in some way, and the columns represent features of it. So in this case, we have each row represents a measurement at a time, a set of measurements at a time, and the columns represent different weather variables: temperature, humidity, dew point temperature, rainfall, wind, and so on. So we read that in like that, and there is our data. So currently we've read it in as a Python list. So to access something in that list, we have to use an index which is kind of arbitrary. What does 1 mean? We don't really know. And that gives us our measurement, and we don't really know what these numbers mean unless we have some external guide to the numbers. What we'd really like is for us to be able to look at this and know immediately all the things that we need to know about it. So we can do this a bit better, we said, using dictionaries. in Python, which associate a key with each value. So for example, if we do that, and now we've looped through our thing, we've read in each row. So now you can see when I access through a dictionary, I've got some metadata. So instead of just saying, give me the values for at index 1, I can say, give me the values at 4 o'clock and give me the value for temperature. And then, so now I know 20 degrees is a temperature at 4 o'clock. So I know a bit more about it. It's a bit more self-describing. And this is basically is what the whole session will be about, making this sort of access easier and more intuitive. This is the basis of a data model. But at this point, we still don't know certain rather important things about this. For example, 20 is that if it's 20 degrees in Celsius, that's a pleasant temperature. If it's 20 degrees in Fahrenheit, that's freezing cold and not very pleasant at all. So the unit is an important piece of metadata to relate that number to the physical world. And so as part of our data model, we might define some things to perform on the data. And at the moment, doing it manually, like we said, is a bit cumbersome. So this is finding the total rain between a certain period of time over our data. And so as you can see, there's a lot of cumbersome code there to do that calculation, not very intuitive. So that's essentially adding up the rainfall values there. I had 16 millimeters of rain in this observation. So what we'd like to do, rather than implement all this ourselves, is use a third-party library that gives us a nice data model. And the standard for tabular data is a library called Pandas. And the data model they use there for tabular data is called a data frame. So let's try loading in that same data, but we'll load it in through a Pandas data frame. So one of the things that Pandas does very nicely is you can read from lots of different sources. CSV is probably the most common, but you can read from, also another very useful one is you can read from a standard SQL or SQL database straight into a data frame. So it has lots of ways of bringing data into the data frame to start with, and that is immediately a very useful feature of the library. So let's see what the data frame looks like. So you can see the data frame in fact also quite nicely provided us with a nice way to visualize the table as well. That's another thing that's useful about using the code that implements a data model has all the features there for you. You don't have to implement that yourself. And so we can see here we've got a nice table at different times, the temperatures at those times, the wind and the rain. And like with the dictionary, we can access that in a fairly intuitive way. So we can say, give me the temperature, and it gives me all the temperature values. So again, we've started to use our data model to think in a more high level way and less have to think about the kind of computer science aspects of the problem and focus on the analysis we actually want to do. So what other common operations might we want to do? We might want to subset. For example, we might say, well, give me all the observations from 4 o'clock onwards. So in this case, you're saying in our data frame, using the time, tell me where the time is greater than 1600 or 4 o'clock, and then give me all elements of the data frame that match that description. And so here we've now subsetted that, and then we could perform further operations on that. There's lots of sophisticated operations you can then do with this whole data model because it knows about it. So for example, let's say I read in some other variables that came in maybe from a different set of instruments. And so this set of measurements tells me the dew point temperature and the pressure. Now, what I can very easily do is I can join those two different sources together using a Pandas merge function. So basically I'm saying merge these two data frames and merge it based on time, which is to say match the 2 o'clock and the 2 o'clock measurements together and the 3 o'clock and the 3 o'clock measurements. And you'll see we've now combined that into a new data set. And because our data model knew about time, it could automatically merge those things based on the time. So we're really starting to work at a higher level and do fairly complicated operations. That would be quite a lot of code to do that manually. from lists and dictionaries. We're just thinking at the high level.
Stephen, sorry to stop you. We've just had a request in the chat to ask if it's possible to zoom in on the screen a bit, just to see.
Yes, thank you very much for reminding me. I always forget to do that.
That's okay.
Thanks for the reminder.
There we go. Right, is that better? Is that okay? If you could let us know in the chat, that'd be great. Brilliant, thank you. Yep, all good. Carry on. Thanks, Stephen.
Super, thank you very much. Yes, any other requests like that, please don't hesitate to ask. Oh. That's useful. Right, so there we are. So now let's start. That's still some synthetic data that I made up. Let's start now looking at some real world data. So this is from a project I've been working on this year. It's a climate data set. It's a tabular data set looking at ocean temperature measurements. This is XBT. XBT stands for Extra Bathy Thermograph, for those who are interested, which essentially it measures temperature and depth. So it measures down through a column of the ocean and it gets some information out. And so I'm just using this data because this one I have access to easily. So we can now read it in. You can see I've got 2 files here from a larger data set. I've just chosen the data for 1989 and 1990. And now I can very easily read in one of those files into a data frame. Hopefully it won't take too long. And so you can see we've got all these elements to our data. So we've got, it tells us the country where the measurement was made, the location and latitude and longitude, the date, the institute that made the measurement, what sort of instrument they used to do the measurement, and so forth. And you can tell useful information, for example, how many data points there are. So we have 45,000 approximately measurements, and each measurement has 22 features in it. And we can see which features those are. So there's a comprehensive list of all the features. Now, a common thing to do with data is you're only interested in a subset of the data. So for example, perhaps for my work, I'm only interested in these features, which is in fact the set of features I am actually using for my project. So in order to use less memory on my computer, I might want to only load a subset. So this is a very common thing you might want to do as a data analyst to be able to manage large data volumes, is only load the things that you're interested in. And Pandas provides a way to do that very easily and quickly by just specifying a list of columns. So it will extract those from whatever data source you're loading it from, like a CSV, and you'll get a data frame with just those things. So now let's load all our data for 1989 and 1990, but only the features that I'm interested in by specifying columns over here. You can see that's specified here. And that should be pretty quick because it's not loading things I don't need. And so you can see we've now got more measurements, 128,000 of them, but we've got fewer features, only the ones I'm interested in. So how can I do some common operations in Pandas on this real world data set? Well, one thing you might like to do is you might be interested in, for example, a particular subset. So let's say for some reason I'm interested in the measurements that were taken in February 1990 for some reason. So I can easily use Pandas to find the data where the year is 1990 and the month is 2, which is February, and see what the data set looks like there. So there I have now extracted very quickly all those measurements. So I've got 7,000 measurements that relate to that February. And so then I might like to do some operations, further analysis to find out whatever it was I was interested in about measurements from that month. And so what other things might I like to do? So another subset operations, there might be some data that I know is a bit dodgy, is bad in some way. Maybe I don't trust the measurements that were submitted, or the institute that was sending them had a dodgy instrument, so it might corrupt my analysis. So I might want to say, extract them. In this case, some of my measurements are, the probe type is unknown, so we don't trust those because we don't trust that they were correctly recorded. So I might say I want to actually say wherever the instrument name contains the string unknown, excluded, so that means not that, and the year was 1990 and the month was February. So if I do that now, you can see I've now reduced it down to 6,000 elements. So 6,000 good measurements on which I can now do something interesting. So I could, for example, say, well, what sort of probe types were used in that month? Here I can see that there were 3,000 measurements from the T4 SIPICAM type probe, 1,000 from the T4 TSK probe, and so on. So I'm starting to gain some insight about my data set very quickly using built-in Pandas functionality. So in this case, it's the value counts function. That's just saying find all the unique elements of type instrument and then tell me how many there are of each of them. So again, that would take a lot of code if I were doing that myself to count that up, and it would be less reliable than this, which has been tested by many people. And then I can perhaps start finding some useful other information. For example, I might want to know how deep each of the probes went, what was the maximum depth they achieved, and what was the average depth over that month. And so you can see that the deepest probe went as far as 1,874 meters, and the average depth was 476. So as you can see here, one of the nice things here is you're not operating on individual elements and looping through. You're just saying, do this to my whole data set, and it converts that into those lower level operations that we looked at in the previous part of the workshop. But if you need to, you can also use Pandas to very easily do things to each element. So for example, let's say I want to convert the maximum depth of each measurement from meters to feet for some reason. Maybe I'm sending this data set to America or something. And so I want to write a function which does that. And then the apply, if I choose a feature, so of my subset, the maximum depth, apply my function, it will then apply this function to every element and give me back a series. So this is a bit like the map function, which we looked at in the previous workshop for those who were there. And so you see I've converted the values from meters to feet for everything. I can also, if you're interested, if you're aware of lambdas, you can also use lambda functions to do the same thing more compactly in Python. I won't go, I think I mentioned lambdas last time, I won't go into too much detail, but it's just a compact way to declare a very small function. And it should give you exactly the same answer. It does give you the same answer, that's good. Now, one thing that's really quite useful then with Pandas as well is how easily you can do some quite complicated plots with your analysis to really gain that insight very easily from a useful visualization of your data. So it could be as simple as in our earlier weather data, we could plot some temperatures. And there you are, you can see how the temperature varied over the course of our data set. Oh, our axis is a bit wrong there. Or you can plot your temperature and rainfall together. So here we can see how the rain's varied over time and the temperature. And you can even do some more sophisticated operations. So for example, the common thing, we were finding the mean maximum depth of a group of, different instrument types. So we might say, I want to find out the statistics for separately for each of the types of probes used to make these measurements to see if there's any difference between them that might have some impact on the scientific work I'm doing. And so there's this useful function called group by. So what this does is it takes our data set, it then takes the instruments that are where they have the values where they have the same value for instrument for that row, puts them into those groups, and then for each of those groups performs the operations. So in this case, for each of those groups, it's going to take the max depth for the profiles in that group, and then find the maximum of the maximum depth for the profiles in a particular group of instruments. And so you can see over here what it's saying for the instrument type Deep Blue Sipican, the maximum depth was 940. And for, say, the T4 Sipican, it was 1,800 meters. But for the T6 Sipican, it was only 400 meters. So this is actually something that I am interested in the project I've been doing in as a way of telling apart different profiles based on maximum depth. So I can find that really quite valuable information very quickly using the standard Pandas functions associated with the Pandas data model. But of course, this only works because I have the metadata associated with it well. So it shows the importance of having the metadata with the data in your data model. And so I can do the same for if I wanted to find the mean depth for each type of instrument just as easily. And I can visualize that nicely as a plot. And so you can see over here that our T5s and tend to go to deeper values, whereas the T6s tend to go to only quite shallow depths. And so we've already gained some valuable insight from our data set very quickly. Right, so I think that's enough on that, just to mention that, so some of the advantages again, so you spend a lot less time writing boilerplate code, and the code tends to be a lot more efficient than code you might write yourself, because obviously this has all been written and tested and optimized by specialists in writing these sorts of algorithms. And it also opens the possibility of working with other libraries. It's become something of a standard for tabular data. So if you use the Pandas interface, you can work with many other useful libraries and tools, such as, for example, Dask, which we'll be looking at in the last section. For those of you who've worked with databases before, you might have noticed there's quite a few similarities between operations in Pandas and in a SQL database. And for those who are interested, I've included some links which gives you more information about the similarities between databases and the Pandas data frame. But for now, we're going to move on to look at gridded data. So this is the same thing now, but we're going to look at it for gridded data. So gridded data, just to recap, is a two-dimensional, not necessarily two-dimensional, can be more, but for this discussion, two-dimensional data representing an atmospheric or oceanic parameter, or along an evenly spaced matrix. So not necessarily only atmospheric or oceanic, but that's probably one of the most common uses. And an evenly spaced matrix. So rather a row with different features, the whole grid represents a single measurement together, essentially. So it could be the weather over the UK, for example, as we're going to look at in a moment. And for the matrix to be useful, ancillary information about the grid must also be known. For example, where is it? What latitude and longitude is it? What time was the measurement taken? And so that together is called a grid object. So we are going to now look at how you can use a standard library for this. So whereas we use Pandas for tabular data, one of the standard ways of working with gridded data is the Iris library, which in fact is a package originally developed by the Met Office, but now there's a whole community around using Iris across the world. And it's a sort of standard for working with meteorological data and other earth science data as well. And it can read from several formats. So we use CSV data for tabular data, but a standard format for gridded data is rather the netcdf format. And so each of those grids, as I said, represents a single physical phenomena, such as temperature or humidity or rainfall. And so a netcdf file then is structured differently to a CSV file, and that Each file may contain several of these grids representing different phenomena or times and so on. And so Iris translates the sets of grid into things called cubes. And so each cube in Iris represents one phenomenon, as we'll see in a moment. And so to demonstrate, I'm going to look at some weather and climate data sets produced by the Met Office. So one is called UKV, which is our high resolution weather forecast model over the UK. So over the UK, it's a 2.2 kilometer square grid cell, and there's the whole of the UK is covered in these grid cells, and those grid cells are used to calculate the weather across the UK. And this is basically what is used as the input to our Met Office weather app. So what does it look like to actually load that data into Iris? So there's the path to our data. See, I've got some variables that I've got. So I've got pressure, rainfall, temperature, maximum and mean, and wind speed. So let's have a look at what temperature looks like. So if I load all the files in the temperature directory, I will then get a cube, which will look like something. Let's see what's in my cube. So Iris provides this nice way of displaying what's in our cube. And we see that we have a grid, so it's a 3-dimensional rather than 2-dimensional grid. It's got latitude and longitude, but it's also got time. So it's got 30 different times of measurement of the temperature phenomenon within our cube. And so it's combined 30 different files, each one representing a time, into a single data object and a data model, which we can work with intuitively and easily, like we did with our Pandas data frame. So let's have a look at what we have in it. So we have 30 times 800 different different latitudes and 621 longitudes. And one of the things that we obviously often want to do when we start working with some data, we want to look at it literally, and as in we want to visualize the data to just sanity check what we've actually got. So let's, for example, visualize some temperature. So this temperature is this data set is from November 2019, and so we can see here. Oh, hold on, let's redo that. Sorry, I've forgotten to clear my outputs. Just reloading all the data because I had forgotten to do that. And in a moment, we will then use the Iris quick plot. So much like Pandas had some functionality for plotting very easily, Iris does as well. And so here I can use quick plot to do a filled contour plot of the first of my temperature times, adding some coastline so I can see where it is. And so here is our weather data. And you can see here's our temperature scale. So you can see obviously it was unsurprisingly colder over the mountains of Scotland than it was in southeast England for the first day of the month. This was the maximum temperature for that day. So that's our weather data set, and we can very easily do a climate data set as well. So UKCP, or UK Climate Predictions, is the latest set of predictions for what the UK climate will look like over the next 100 years or so, based on a large ensemble of climate simulations. The difference between the weather and the climate data set is we're not interested in instantaneous values for climate data. We're more interested in averages over longer periods of time. So let's load in some climate data. So we've got some variables. We've got precipitation, pressure, wind, maximum temperature, minimum temperature. So let's have a look at what the precipitation looks like. So we've got the daily rainfall over a year for 600 latitude points and 480 longitude points. And to match the same information, so we've got some good metadata here, which tells us useful things. So, for example, the units are millimeters per day, which tells us something about it. It tells us where all the data comes from. So this is all good practice in creating a data model, is to store all that metadata with the data, so you know what the numbers in your data actually mean. And similarly, we can quickly plot and see what our data looks like. And so you can see here's some precipitation from one of our simulation runs of rainfall for a particular day. But like I said, we're not actually interested in per day with climate models. We're interested in averages. And so we'll have a look now at how you can get your longer term meaningful information out of a climate simulation. So how does Iris allow us to do that analysis and visualization very easily? So let's say we probably want maybe to find what was the total rainfall in different areas of the UK over our whole 1 year of simulation of rainfall. And so Iris can do that very easily using some analysis functions. So in Iris terminology, you use this function called collapse. So essentially you're collapsing one dimension of, or more dimensions of, your cube to using some sort of operation. So it may be a sum or an average, so that you're only looking at, in this case, we're going to average over time. And so we'll only have latitude and longitude dimensions left. And so it's very easy. So you can see, say, collapsed. I want to collapse it by summing. And then I'm going to feed that into a plot so I can see what the result is very easily. So it'll take a little bit longer to do because it's having to do a little bit more work this time. And here we go. So over a year of simulation, you can see how rainfall differed over the UK in our simulated year. And you can see here the units. So unsurprisingly, there was much more rain in northwest Scotland again than eastern England. And we can see that based on the scale, there was over 2,800 millimeters of rain in places in western Scotland, where parts of East Anglia had less than 400 millimeters of rain in our simulation. And so we were very easily able to extract that climate information from our simulation and do some analysis very easily using the functionality, the collapse functionality of Iris and the sum function. So in this case, that example, our file contained only a single time and a single phenomenon, but you can also store files where you have multiple grids together and multiple times all together. Iris can also do that and then get a whole list of phenomena out. So for example, if I do this, you can see I've now loaded, with the Iris load function, I've now loaded a whole list of things, and I have several different phenomena. So now I've got air pressure at sea level, temperature, max and min and mean, and I've got some rainfall and some wind speed and some wind gust information from my simulation. This is now the weather data again. And Iris enables you to very easily, if you've got a large amount of data in a file, as we did with Pandas, you can only load the things that you're interested in. That makes it much easier to manage data volumes. So for example, say from this file that's got lots of stuff in it, give me just the air pressure values. And now we should have only a single phenomenon, which is air pressure, again, like we did before. So again, subsetting is often a very important part of the work you do as a data analyst. To zero in on the part of the data that's of most interest to you. So let's say, for example, we were wanting to study some aspect of the weather over Devon and Cornwall. So maybe you wanted to get a particular subset of that data. So here I've entered the values to extract just the part over Devon and Cornwall, and then plot that for the maximum temperature in our forecast. Let's see what that looks like. So there you are, very easily extracted only the bit of the data set that I am interested in. So you can see there's where I am in Exeter, and there's the southwest peninsula of the UK, or Great Britain. And the temperature within that. So zoomed in, we can see a bit more in the way of detail. And again, so we can now do some sophisticated operations. We don't have to manually go through our cube and iterate through the for loop. We can focus on very high levels. So for example, let's say what I was interested in was the diurnal temperature range, just to say what's the difference between the maximum and the minimum temperature each day. So here I've subtracted minimum from maximum temperature using Iris. Iris then does all the calculations without the data model that it has and the data, and it uses that then to create a meaningful plot. Hopefully it creates a meaningful plot. There it is. So we can see here now we've looked at diurnal temperature range for the whole of the UK, and we can see that there was much more difference between maximum and minimum for this day of our forecast in East Anglia compared to Southwest England. So we've potentially gained some insight from our data there using these very useful high-level functions provided by Iris. Another useful thing to extract from gridded data is you might want to say what is happening at a particular point in space, but over time. So looking at a different set of dimensions, not a range of latitudes and longitudes averaged over time, but a particular latitude and longitude over the full extent of our simulation. So you can easily extract and plot that using Iris as well. So in this case, since I'm interested in diurnal range again, I'm going to pick a particular place. In this case, it's the area around Exeter. I've extracted that using the Iris constraint. So the Iris constraint gives you a subset. I should have mentioned that earlier, sorry. And then I'm going to do the collapsed again. So I'm going to find the mean temperature for that little area around Exeter in the UK. And then I'm going to plot that time series that's come out having averaged over the latitude and longitude, and I'll compare maximum and minimum temperature, and let's see what our plot looks like. And there you are. So very easily I can extract some quite meaningful information. So this, for the area around Exeter, the average maximum minimum temperature in that area over the full course of our forecast. So it starts a bit higher, and then it goes down over time, and then it goes up again. And you can see how some days there's a larger difference between maximum and minimum compared to other days where it's quite close together. And so using that data model, I can very easily and intuitively work with the data to gain insight and visualize that insight as well. So that kind of sums up what I want to say about data models. I just thought I'd mention something now about kind of what's going on under the hood, because the data models are doing some clever things with the code to make it easier to work with data. So firstly, obviously, they've got this nice data model with metadata, but somewhere underneath there must be some actual numbers. So in the case of our Iris cube, if I use the .data attribute of the object, you'll see that it's ultimately just a NumPy array, which we looked at last time, but it's using it in a cleverer way. And so you can work with that if you want to, but again, we want to rather avoid working with that and use our nice data model to work more intuitively. It also has some metadata. So in this case, it has coordinates to tell you where in the world our data represents. So in this case, it has a time coordinate representing the different days in our forecast. It has latitude and longitude, and there are some various other things which are not actually really used in this case because it's a surface phenomenon that we're looking at here, so we don't have to know the height in the atmosphere. But if you are looking at wind more generally, you are often interested in weather in winds at different altitudes. So for example, for forecasts for pilots, you don't need to know not the wind on the ground, but the wind at certain levels in the atmosphere, depending on where you're going to be flying. So it can tell you that too. And so ultimately, those are just numbers as well, but it's that relationship between the data, as you said in the introduction about data models, that makes it a data model, because it's saying these latitude or latitude values represent the location of these temperature values. So it's defining those relationships. Another thing I mentioned a little bit last time is the idea of lazy loading, where you you perform an operation but don't actually perform the operation until later. It's the concept of a generator, which is essentially an IOU, a contract to say, I'll do it later. Now, you might say, why do I want to do that? If I want the data, I want it now. But there are some very useful reasons for doing that. And Iris uses a library called Dask to implement that. So I won't go into too much detail, but it's quite useful. If I now load one of these cubes, you'll see that it doesn't actually load the data until at this point, it's only set up the computation to do later, and only when I actually want to do the calculation here does it actually load the data. And here is our calculation. So this is quite useful because that computation object, which says I'll do the computation later, could actually then be running on a different computer from where you set it up. And so this is an important idea in big data, to be able to use, say, cloud computing or a big server to do your computation. This allows you to do that sending to a remote computer very easily. And so in that way, Iris's data model allows you to be more efficient at using the compute that's available to you. So before I move on to our final part, are there any questions quickly? I see time is getting on, so I should probably get on, but don't hesitate to put the question in the chat if you have anything, and I can answer as we go along. So that's kind of the most of the content for today. I've just created a notebook, which I won't go into any great detail here. It's more kind of for reference for future. Hopefully, if you've gotten to this point, once you can load your data into a data model, you're in a position to actually do the analysis. And I think once you get to that point and you have that level of familiarity with how Python works, you can. The rest is often not easy, but it's easier once you have that foundation. But I thought I'd mention some libraries for how to take your data analysis to the next level and work with some real-world data sets. So one library I mentioned previously is Dask, and this is a way to handle big data sets. So we used Pandas to load our tabular data set, but you can also use Dask, which has the same interface as Pandas to a tabular dataset, but it does more of this lazy loading to be clever about it. So if you've got a really big dataset, now this dataset is not particularly big, but if you have a really big dataset, it does clever things, because you see, if I go load, when let me clear that. So now I'm loading my data as I did before, but you'll see it doesn't actually have anything in it at this stage. It's only loaded the metadata. And that's quite useful because let's say this was a 1 terabyte file, which I can't fit into memory. If I tried to load it now, I'd just be sitting around waiting forever and I wouldn't be able to do anything. Instead, what I can do is I can set up my computation. So for example, let's say I load more of my data. And now I want to join it into a single data frame. And then I want to extract certain of the profiles based on the instrument type. And then do the same calculation we did earlier, which is calculate the mean of the max depth for that instrument type. It's not actually done any computation. So that computation might be really slow, so I can set it all up. And then only when I say compute does it actually do it. And very useful using various bits of functionality from Dask, you can have that execute on a completely different computer, on a cluster using something from a cloud provider. And so if that's a really big data set, that's important because you might not be able to handle on your local laptop or desktop. And so Dask provides a facility to work with these big data sets and data models very easily using sophisticated computing resources. So when I do that, now is when it actually does the work and gives me the answer. Also to mention, I'm sure many of you have heard of cloud computing. One way to deal with a huge data set is to use a huge computer. And that's essentially what cloud computing provides. It's somebody else's big computer and you pay for the time that you use on it. That's essentially cloud computing in a nutshell, which is often presented as new, but it's not actually a very new idea. It's essentially the same thing as timeshare computing, which happened all the way back in the 1970s, but it's obviously a lot more powerful now. And there's lots of useful services. So there's just a list of some of the many, many cloud providers available. Amazon Web Services is probably the first cloud provider. Microsoft does it, Google, there's various third-party providers such as DigitalOcean, and many, many other cloud providers available. So what are the advantages from point of data analysis for this? Well, one is burst workflow. So often when you're doing analysis, you're not constantly running jobs. So if you had to buy a really expensive computer to do data analysis on, you're probably only going to use it some of the time. So that's very inefficient. Whereas rather, on the cloud, when you do the data analysis, you pay for the compute you use for a short burst, so you can get lots of compute for a short time, and it doesn't cost you a lot of money. And because it's sitting around idle the rest of the time. And scalable, so kind of almost instantaneously, you can get access to compute resource to do your analysis when you need it, and of whatever sort you need. So if you need lots of memory, that's available. If you need GPUs, that's also available. And another big thing, particularly for developers, is that it provides you with the managed environment. So if you're going to be running through these notebooks, you'll have to set up an environment yourself using Conda or something. Or you can use a cloud provider where those things are done for you. So you spend more time on doing your analysis and less time on all the software maintenance stuff. So that's a big advantage. That's one of the things you're paying for with the cloud provider. And the last thing I mentioned, I won't go through all this now, but there are also lots of other ways of creating very rich visualizations which help you do your analysis. So one library I've used is called Bokeh. So unlike Matplotlib, where you provide creating essentially a static image of a plot, with Bokeh, you can do all sorts of interesting interactive visualizations. So for example, let me import this here. So this is just a very simple graph to demonstrate it. Uses a fairly similar sort of interface to Matplotlib. So I've created some data, said plot me a line with X and Y, colors and so forth. This is just taken from the standard Bokeh documentation, by the way. Then what's different is I create a function, which is where the plots happen. And then I tell Bokeh where that is so that it can update the plots as it goes along. So there's our plot, but now instead of it just being a static figure, if I run this piece of code, I can change what's happening here. And so as I do that, oh, that's not very good. well, that's the peril of live demos. In theory, when I move this over here, the values in my plot will have changed. Now, the virtue of that is because when you have a big data set, there's usually not just one plot you can do which tells you everything you want to do. So the person looking at it might want to interact with it and say, oh, show me things for different areas or different times, and interactively the plot will update, and so you can really interrogate your data very easily. So I should probably stop there. I could go on all day talking about the very many different tools there are to really get stuck into analyzing your data. If you have any questions about what tools might be right for you in Python, don't hesitate to get in touch via email. Happy to give you some pointers towards what will be useful for your particular problem, or feel free to ask some questions now. But yes, otherwise, thank you for joining us for these 2 workshops on Python for data analysis. I hope you've found them to be useful and got an idea of how Python can be useful for analyzing your business data. Don't hesitate to get in touch with further questions.
Thank you very much, Stephen. And as Stephen said, if you've got any questions, then do let us know. I'll make sure that I send out the recording to this session when it's ready, and any links which were mentioned in this session as well. And yeah, thank you again. And when it comes around, have a lovely festive season. Bye-bye.
Thank you.
Bye all, thank you.
Bye.